Welcome to this week 8 TS session on constraint and unconstrained optimization. In this week also I'll be discussing some of the assignment questions that was posted last week. So those will be assignment 8 discussions. So answers I think already been posted, but I'll go through the solution once more. And then I'll be talking about some of the similar problems that you'll find in assignment 9. That will be the main discussion in this sessions. And yeah, later if anyone have any doubts, they can always post it in the discussion forum or can ask me. We'll be continuing our discussion with this nonlinear programming problems. And mainly the focus in this week will be to deal with unconstrained optimization problems. Okay, so without further delay, I'll get started. So the topics that I'll be covering in today's session, first one will be week 8 assignment solutions. And next will be similar problems to week 9 assignment. Okay. And the discussion will be generally very short, I guess. It might not go till 2 hours because of the problems being easier and so on and very similar to each other. But anyway, let's see how much I can cover. Okay, first I'll get started with this week 8 assignment solutions. Okay, so let me write down the questions as well as answers so that you can see it later, you will be able to understand. Okay, the first problem is, I'll write down the problem. So it says for minimization problem of a unimodal function. So I guess you already know what a unimodal function is, which is basically one mode, and it has only one local optima or local minima or local maxima within that interval. Fx, where so x belongs to this closed interval AB, and let us take 2 points x1, x2 that also belongs to this interval. Then which of the following is or are true? Okay, so let me write down the options. First one is if fx1 greater than fx2, then minimum of fx lies within this interval x1, x2, or option B is if you have this fx2 greater than fx1, then minimum of fx lies within ax1. Option C tells you that if fx2 is greater than fx1, then minimum of fx lies within ax2 and option D is if fx1 is equals to fx2, then minimum of fx lies within x1 comma x2. Okay, so that's your problem statement, and let me try to solve it. So this is the problem that you have and the options. Okay, so the answer. Now, first, what you have to check is that you are solving a minimization problem of a unimodal function fx. So let me draw the function. So this could be the fx, and this is x. Since it's an unimodal function and you're solving a minimization problem, so it will have this one minima somewhere here, and the interval is a1 and a2. Sorry, it's a and b rather. So this is a, this is b. Now you'll be picking 2 points x1 and x2, and based on the conditions, you have to check which one occurs, right? So let me first is say case 1, fx1 is greater than fx2. Okay, so what you can do is you can take x1 to be somewhere here, suppose, and x2 to be probably somewhere here. So as you can notice, this is your minimum point. So within this region, you know that this is decreasing, and after that, you'll have somewhere this is something which is also decreasing. So what you can do here is you can exclude this portion actually, and you can work with this new interval x1 to b, and the minimum will lie there. Even if you had picked your x2 somewhere here, so probably this can be your x2 9 or something. So there also you could have just excluded the left portion, say from a to x1, and the rest of the portion could include your minimum point. Okay, so here in this case you can exclude ax1 and minimum lies within x1 to b. Okay, so let me check if this is indeed any option is there. The first option is not true then, because that's the only condition. So let's check the second condition. So let me check case 2. Okay, and you can notice that you could not have picked x1 in this right portion of this minimum, because this part is an increasing function in that region, right? Okay, so anyway, let's get into the second case. Fx2 is greater than fx1. Let me sketch the function again. This is fx, this is x. Okay, so this could be your minima. This is your a, this is your b. Now x2, fx2 is greater than this fx1. So let me pick my x1 somewhere here, suppose, and x2 somewhere here. In this case, you know that you can exclude this portion because this part doesn't include the minima, right? Or like you could have taken your x1 here as well. In that case also you could have excluded this right portion, but you couldn't have taken your x1 and x2 both on the left to the minima, because in that case fx1 would have been greater than fx2. So in this case, exclude x2 to b, and minimum lies within a to x2. Let's see if any option is correct. Yeah, option C is correct, right? Now let's move on to the final one. Case 3, which tells you fx1 equals fx2, and obviously x1 is not equals to x2, so that's kind of implied. And let me draw the function again. This is fx, this is x. Okay, so this is your a, this is your b. Now you have to pick 2 points and then guess that it will be two sides of this minima, right? So if you're picking your x1 here, so your x2 will be somewhere here and both are equal. In this case, what you can do, you can exclude this one because you know that it will have an increasing trend from here onwards, and you know the decreasing trend, and from here you will have an increasing trend. Okay, so you can exclude ax1 and x2b here. Okay, and minimum lies within x1 comma x2. So let's see if any option satisfies that. Yeah, so option D is also correct. Okay, so for this problem, you have this answer as C and D, right? Okay, so that's all about the first problem, and I think it's clear to you now. Let me move on to the second problem and solve it. Okay. Okay, so the second problem tells you to solve a problem, an unconstrained nonlinear optimization problem using interval halving method. Okay, so I think you have already gone through this in the lectures. Okay, so find the minimum of fx equals x times x minus 1.5, x belongs to 0, 1, within 10% of exact value using interval halving method. Okay, so let me write down the options. Option A is x star equals 0.75, f star equals minus 0.5625. Option B is x star equals 0, f star equals 0. Option C is x star equals 0.6875. F star equals minus 0.5625. Option D is x star equals 0.8125 and f star is minus 0.558594. Okay, so let me solve this problem now. Okay, so for this one, first what you have to do, uh, notice that 10% of exact value. So that's the keyword here using interval halving method. So you need to determine how many points or how many function evaluations you have to make here in order to achieve this. So let me just quickly check what is the formula. Yeah. So for this interval halving method, what you have is half times ln by L0. This should be less than equals 1 by 10. And here this ln by L0 is half times n minus 1 by 2. This is less than equals 1 by 10. Okay. Then what you can do, you can take this as 1/5, or you can take 2 to the power n minus 1 by 2, the greater than equals 5, and now you can take this as greater than equals 3, and that will give you n is greater than equals to 7. So minimum number of okay, minimum number of points required equals 7. Okay, so that's fine. Now let's do this actually, like which 7 points you require. So in the interval halving method, what typically you do it is you half your interval after every iteration. So your initial interval here is 0, 1, and the length of the interval here is 1. But in the next iteration, when you will do it, you will probably shrink your interval to zero 0.5. So that will be the length of your interval. Okay. So let me do this now. Okay, so just let me check one thing. Yeah, so let me sketch something, some function. Need not be this function. So I'm not showing how the nature of this function looks like. But because at 0 it will be 0, I think. But okay, 0 it will be 0, 1.5 it will be 0. Okay, so at 2 it will be 1. Okay. And in between it will be negative. Okay, so you might encounter something like probably this could be your function now, and yeah, you can extend it in this side as well. but uh, let's not do that. Okay, so okay, anyway, this is 0. So this is 1.5. So probably this is your point, which is 1. So x belongs to 0, 1, that you already know. Now you have to find the minima within this interval. So in order to do that, what you can do, you can take two more points and you have to evaluate the function, or you can take actually 3 points and you have to evaluate the function expression or the function values at those points. So what you can do, you can take something here, here, and here. So this could be your 0.25, this could be your zero point 0.5, this could be 0.75. And now you will do function evaluations at this 3 points, and then based on the values of this function at this say x1, x2, x3 points, you can eliminate two of these regions and you can halve your interval. So that's the idea behind this. Okay. So let me write down. So just a minute. Okay. So this is x1, this is x2, this is x3. So these are your 3 points. Then f1 will function value, f2 and f3. So these will be your function values. So in the first iteration, what you can take x1 as 0.25, 0.5 and 0.75. And you know your function expression is x times x minus 1.5. So the values, if you calculate, you will get 0.3125 here, minus 0.5 here, and minus 0.5625 here. So it has a decreasing trend even after 0.75. So what you can say for sure that you can eliminate uh, this region, which is 0 to 0.5 in the first interval halving method's first iteration. Okay. So you can say eliminate 0 to 0.5. Okay, so in the next iteration, what you can do, you can take, so you know that you are dealing with an interval which is 0.5 to 1, right? So this is your new interval. And again, you have to break it down into 4 like equal intervals to get 3 points. And the 3 points will be 0.625, 0.75, and 0.875. And the function values at this point will be 0.54688 minus 0.5625 and minus 0.54688. So from here, what you can tell that from 0.5 to 0.625, probably it has a decreasing trend because from 625, 0.625 to 0.75, it has another decreasing phase. And then it has an increasing phase in this 0.75 to 0.875. So actually, so it's very similar to before. So at 0.625 and 0.875, so if you consider those 2 points, you have equal values at those. And that means your minima will be lying within that interval 0.625 to 0.875. So that means you can eliminate. So you notice you just halving your interval at every iteration. So you can eliminate 0.5 to 0.625 and 0.875 to 1. Okay, so that would be your iteration 2. Then in the next iteration again, now you're dealing with something in this form. Again, you have to take or make it 4 equal intervals to get those 3 points. So the points are 0.6875, 0.75, this remains the same, and 0.8125. And the function values are minus 0.55859, minus 0.5625, and minus 0.55859. So here also it's very similar to the previous one. So you can say that eliminate this 0.625 to 0.6875 and 0.8125 to 0.875, right? So the new interval that you will be getting from here is 0.6875 to 0.8125. And the midpoint is 0.75. And you can notice that you know that minimum will lie in this interval. And if you just consider the midpoint, you are within the 10% of this exact value, right? Because the interval length was 1 and you were within plus minus zero point 0.1 anyway. And actually it's lesser than that. So that's fine. So this you can take it as your x star, and your f star will be the value at that point, which is minus 0.5625, right? So this will be your solution to this problem. Now check whether you have indeed taken this 7 points or not. Okay, so let me write it down with using this color. So this is your first point, this is your second point, this is your third point, this is your fourth point. This 0.75 is already taken, so this one is your fifth point. This is your sixth point. 0.75 is again taken, and this is your seventh point. So indeed you are dealing with 7 points to get to that 10% of this exact value. Okay, so that's the idea behind this problem, and the solution to this problem will be this one, x star 0.75 and f star this one. So option A is the correct answer here. Okay, so I'll just write it down once more. So answer is A, which is x star equals 0.75 and f star, which is minus 0.5625. Great. Okay, so that's all about the second problem. Now let me move on to the third problem. Okay, so the third problem tells me find the, so now you will be dealing with a similar problem, but it is now using an exhaustive search method. Okay, so here it tells me find the minimum of fx equals x squared minus 1.5 x plus 5, and the interval is again x belonging to this 0, 1 closed interval within now 10% of exact value using exhaustive search method. Okay, so the options are, the option A is x star equals 0.45, B is star equals 0.75, C is x star equals 0.9, and option D is x star equals 0.5. Okay, so let me solve this problem. Okay, so for this problem, the key thing is that you are again dealing with 10% of exact value using exhaustive search method. Okay. Now let me check how many points you require for this one. So I'll just write down the expression for this one. Yeah, so for exhaustive search method, what you have to do, it's 1 by n plus 1 is less than equals 1 by 10. So that means n plus 1 is greater than equals 10, and that means n is greater than equals 9. So that means minimum number of points required equals 9. So that means you will be dividing your interval 0 to 1 in exactly 10 equal intervals or sub-intervals. So that way you'll get 9 intermediate points. So what you have, suppose this is your 0, this is your 1. This will be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9. So you'll get 9 points in between. And at all these points, so this is your x, you have to evaluate your f values, which is your function. So your function is x square minus 1.5x plus 5. So let me create a table. So this is your x values and this is your f values. Okay, so and you can also find out on 0 and 1 points as well. Okay, so at 0 it's 5.1, it is 4.86. So let me just quickly check whether I'm doing it correctly or not. Yeah. Then it's at 0.2, it is 4.74. At 0.3, it is 4.64. At 0.4, it is 4.56. At 0.5, it is 4.5. At 0.6, it is 4.46. At 0.7, it is 4.44. 0.8, it is 4.44. So at 0.9, it is 4.46. And at 1, it is 4.5. Yeah, I hope these calculations are fine. So you can notice that uh, this function is decreasing till this, say this 0.7, and then again at 0.8 it is same. 0.9 it is again increasing, so this is the decreasing part. So again this is the increasing part. So as before, we're solving a minimization problem. And since, so f 0.75, sorry, f 0.7 equals f 0.8 equals 4.4, and the assumption it's an unimodal function, so that means minimum lies within 0.7 to 0.8. So what you can take the mean, which is 0.75, and you can treat it as x star, even though when you pick 0.75, it's within 5% of the exact value, because uh, you know for sure that it's within 0.7 and 0.8. But typically what is being done here is that the one with the minimum generally is being picked. So if this one is the minimum, then generally we look at the interval before and the interval after that, and we know for certain that it will lie within 0.6 and 0.8 in that case. But you could have also picked here this one, right? And you could have said that it lies between 0.7 and 0.9, but since we have two values which are exactly equal to each other here, so we can further shrink it and make call that it will definitely be within 0.7 and 0.8. So anyway, so that percentage value, it's a bit confusing, but this will be the right answer here. So x star will be 0.75 in this problem. So in that case, so option B is the correct one. So I hope this is clear. So this was using exhaustive search method. So answer is option B, which is x star equals 0.75. Okay, so let me now move on to the fourth problem. Okay. Yeah, the fourth problem is a simple problem. So it asks you about the dichotomous search method, and it only asks you to tell the minimum number of iterations required for 10% accuracy in dichotomous search method. Yes, the options are 6, 4, 8, and option D is 5. Okay, so let me solve this problem. Yeah, should not be too difficult. So I'll just quickly check certain things. Yeah. Okay, so we know that we have a relationship between ln and l0 in dichotomous search method. So, so the keyword here is that 10% accuracy in dichotomous search method. Okay. Now we know that in dichotomous search method, we have ln equals l0 divided by 2 to the power n by 2 plus delta. So delta is the very small shift that you take from the midpoints, right? Delta by 2, those things. So this delta times 1 minus 1 by 2 to the power n by 2. So this is directly from the slides. So I have used this. But what you can do here is that you can approximate to say L naught by 2 to the power n by 2 since delta is very small. Now, as before, what you will be having half times ln by L naught less than 1 by 10. Okay, and this ln by L naught, so this is half, this becomes 1 by 2 to the power n by 2 less than equals 1 by 10. So what you will be left with is less than equals 1 by 5, and after that it's n by 2 greater than equals 5. Not 5, sorry, it's let me write down it this way: 2 to the power n by 2 greater than equals 5, and you know that n will be an even number, so n by 2 is greater than equals 3 here, so 2 squared won't be sufficient. In this case 2 cube will be uh, just a minute, yeah, so 2 cube will be sufficient, right? Okay, so n will be greater than equals 6 in this case, so this is the minimum number of iterations required. This is equals 6. Let me check which is the correct answer. So option A will be the correct answer here. So that was pretty straightforward. Okay, so not much to understand. It's basic things only. Okay, so that's all about this fourth problem. Now let me move on to the fifth problem. So the fifth problem tells you, so this is again related to the dichotomous search method. And now we have a function that you have to minimize, and the delta values and everything are given. So in this problem, what is written is the interval of uncertainty. So I think you have already known what an interval of uncertainty is from the slides and also from the lectures. After first step of dichotomous search method, for minimization of if x equals x square minus 3x and x belongs to 1 comma 2 here, with delta equals 0.001 is, so option A is L1 equals 1.4995 comma 2, B L2 equals 1.4995. So actually the first one also it should be L2 because we don't deal with L1s anywhere in dichotomous search method because it's the even numbers that we deal with, right? So this is another one. Option C is L2 equals 1.500 comma 2, and option D is L2 equals 1.495 comma 1.565. Okay, so now let me solve this. So it's an interesting problem to deal with. So let me write down the expressions. So fx is x squared minus 3x. X belongs to okay, x belongs to 1 comma 2, delta equals 0.001. So in dichotomous search method, what is typically being done here is that, so suppose this is 1, this is 2, this is 1.5, and now we'll be picking x1 and x2 like this. So this is a equals 1, b equals 2. So L naught initially is 1 minus 0, sorry, it's 2 minus 1. 2 minus 1 equals 1. So what you can write, x1 is a plus half of L naught, which was the length, minus delta, and x2 is b minus half L naught minus delta. Okay, so the values are given. Now it's time to find out this x1 and x2. And then you'll be getting the interval of uncertainty after the first step. But yeah, you have to do some function evaluations before that. So x1, it's a is 1 plus half times 1 minus 0.001. So it's 1.4995. Okay, x2, it's 2 minus half 1 minus 0.001. So it's 1.5005. Now let's do function evaluations at this point, x1 and x2, as well as at a and b. So let me do this. I can create one table. So this is your x values, and this is your f values. So x is 1, and then the function value is minus 2. So if I'm not wrong, yeah, so that's fine. Now you have to find out 1.4995 here. It decreases to say minus 2.25 here. So you can find out this values. Here also it is minus 2.25, and at 2 it is again minus 2. So now you can notice this is the decreasing part. Okay, just a minute. This part is the increasing part, and in between those two are equal, right? So from this you can say for certain that minimum lies within 1.4995 and 1.5005, and you can discard the intervals. So actually in this dichotomous search method, this becomes your interval of uncertainty after the first step. So this is the interval of uncertainty after the first step. Yeah, I hope this is clear, and let's see if there is any option which is correct. Yeah, option B is the correct one here. So your answer is option B, which is L2 equals 1.4995, comma 1.5005. Okay, so this is the correct answer. Okay, so that's all about the fifth problem. Now I'll solve the rest of the 5 problems. So I'll just check how much time I have taken and if it's been recorded or not. Yeah, it's around 50 minutes, so that's fine. Yeah, and it is being recorded. Okay, just I'll have some water and start. Okay. Okay, so let me start the 6th problem. Okay, so the 6th problem, it's asking you for the reduction rate of the initial interval in the Fibonacci method. Yeah, so the Fibonacci method, I think you have also studied it in the lectures and also in the slides. I think you'll find this answer directly, but yeah, I'll just write it down. So the answer, I'm not going into the proof of it because that's already been done in the class. And it's present in the table that was there in the slides. Okay, so the of reduction rate of the initial interval is not a comma b in the Fibonacci method is given by, okay, so options are fn, option b is 1 plus 1 by fn, option c is 2 by fn, option d is 1 by fn. So I'll just check one thing here. Okay, so the correct answer here is option D. Check slides, so I'm not going into the details. Okay, so 6th problem is straightforward. 7 and 8 is also straightforward, but yeah, I'll just write it down. Okay, 7th problem tells me in golden section method, x1, x2 belongs to say AB and equals L0. L0 could be the length of the interval is obtained as so you know that this golden section method is very similar to the Fibonacci search method. So, but you have this golden ratio term that's being included here, right? So these gamma is the golden ratio. So the value of gamma is being asked here, and again it's directly from the slides, and the proof of this has already been done. So I'm not going into the details of it. In golden section method, is given by okay, so the option is A gamma equals 1.861, B is gamma equals 1.681, C is gamma equals 0.618. So you know that option C will be the correct one here. Straightforward. Okay. So actually option C is the correct one. And you can write down the answer. So that's option C, which is gamma equals 1.618. Okay, so problem 8 is again directly from the slides itself. So I'll write down the problem. So this is 8. So for 10% accuracy, which of the following statements is or so again it's comparing the Fibonacci search method and the golden section method. Okay, so which of the following is or are true? The options are Fibonacci search method is preferable over the golden section method, is preferable over the golden section method. Okay. Option B is golden section method is preferable over the Fibonacci method. So it depends on how many points at which you have to do those function evaluations, and again it is dependent on the reduction rates and so on. So it has already been proved in the class that which one is better for what accuracy. The third option is Fibonacci method and golden section methods are equally preferable. Option D is none of this. As you already know from the slides, option A will be the correct answer because it requires lesser number of points for the Fibonacci search method. So answer is option A. However, you need to keep in mind one note. So I'll write down the note. For 5% accuracy, golden section method is preferable. Golden section method is preferable over the Fibonacci method. So based on accuracies, the number of points that you require may vary, and this is one thing you have to keep in mind. Okay, so let me move on to the 9th and 10th problem. So after that, this week 8 assignment will be solved. Then I'll move on to the similar problems to week 9 assignments. Okay. So this is the ninth problem. So the ninth problem tells you the interval of uncertainty, interval of uncertainty after first step, after first step of Fibonacci method for minimization of fx equals x square minus 3x plus 2. Okay, so x belongs to 1 comma 2 with n equals to 6 is, so now we have to solve it using the Fibonacci search method. So the options are L1, and you have to find the interval of uncertainty. Okay, this is the first option. Option B is L1 equals 1.4995 comma 2. Option C is L1 equals 1 comma 1.3846. And finally option D, which is L1 equals 1.3846 comma 2. Okay, so let me solve this problem. So what's given here is this function expression, x square minus 3x plus 2, x belongs to 1 comma 2, and n equals to 6, which is used in Fibonacci search method. Okay, so what I can do, first I'll write down the Fibonacci numbers. So f0 is 1, f1 is 1, f2 is 2, f3 is 3, f4 is 5, f5 is 8, and f6 is 30. So up to this, it will be required in this problem. And in this Fibonacci search method, what is typically being done is, this is A, this is B. So your A is 1, B is 2, and you take 2 points x1 and x2. So this x1 is equals to A plus fn minus 2 by fn times L0, and x2 equals B minus fn minus 2 by fn times L0. Here L0 is 2 minus 1, which is 1. Now let me find out what x1 and x2 is in this problem. Okay, so x1 is 1 plus, n is 4, right? Sorry, n is 6 in this problem. It's 1. So x1 is 1 plus f4 by f6. X2 is 2 minus f4 by f6. It's 1. So it's 1 plus f4 I have written down 5, and f6 is 13. This is 2 minus 5 by 13. Okay. So one is 18 by 13 and another is 21 by 13. Anyway, it will be 1.3846 if you write it down till 4 decimal places. This one will be 1.6154. Okay, so let me now find out the function values at this point. So the function expression is given. So I'll create another table as before. This is x, this is f. So at 1, the function value is 0. At 1.3846, the function value is minus 0.23669. So it has a decreasing trend. At 1.6154, it has also a value of minus 0.23669. And at 2, the function value is again 0. So this is the decreasing part. This is increasing part. And the function values are equal at those 2 points. So that means minimum lies within 1.3846, 1.6154. So this will be your interval of uncertainty after the first step. So this is nothing but interval of uncertainty after first step. Okay, so I hope this will be clear. And let me check which one is the correct answer. So option A is the correct answer here. So let me write it down again. So L1 is 1.3846, 0.6154. Okay, so that's all about the 9th problem. Now let me uh, move on to the final problem in this assignment, which is the 10th problem. Okay, so the 10th problem tells you if p of x equals a naught plus a1x plus a2x square is the quadratic approximation of the function fx in quadratic interpolation optimization method. In quadratic interpolation optimization method, then which one of the following will be true, right? So the option A is a2 less than 0 and for minimization of fx. B is a2 greater than 0 for minimization of fx. Okay. Option C is A naught and A1 are unrestricted in sign. And option D is A0, A1, A2 all are positive, irrespective of minimization or maximization of x or maximization of fx. Okay, so let me solve this final problem. So here what's given is that uh, quadratic approximation. So this px is kind of approximating some fx, right? So that means the minimum of, if you're minimizing this function fx, it should be equivalent to minimizing the function or the polynomial or the quadratic polynomial that you have, px, right? So what you can do here is that you can take the first order derivative p prime x equals a1 plus 2 a2x. So that means, so that's first order derivative. Second order derivative is 2a2x, 2a2, right? Now, for first order derivative, for minimization or maximization problem, to find the stationary point, you can set it to 0 and get x star equals minus 2a2 by u1. Here, this is greater, it should be greater than 0. So for minimization problem, right? For minimization problem. And less than 0 for maximization problem. So that means the sign restriction is only on A2. So A2 greater than 0 for minimization problem. And A1 and A3 can be unrestricted in sign, or A0 and A3. I think. Yeah, A0 and A1. Sorry, A0 and A1 can be unrestricted in sign. Because we don't need any conditions imposed on them. So what you can do, the correct answer here is, first one is not true. A2 greater than 0 for minimization of fx. B is true. Option C is true because A naught and A1 would not be like having any signs or something in particular. And the fourth one is not true because depending on whether it's a minimization problem or a maximization problem, the sign of A2 will change. Okay, so the answer is B and C. This is B and C. Yeah, so I think there were not much of an issue in this assignment. I think except for one of the questions, I think, which is question 3, which had some 10% interval, but you were getting some 5% interval. But I think that's fine. I don't think there should be any issues raised depending like on this assignment 8. So now what I can do, I can solve for some similar problems that you'll find in assignment 9, which will be due, I think, in this Wednesday. So before that, you need to solve it and submit. Okay, so I'll move on to that. I'll just check how much time I have in the session. Okay, so it's around 45 minutes I have. So let me solve some 5 to 6 problems if possible in this session. Okay. Okay. So the discussion is now on similar to week 9 assignment problems. Okay, so let me open assignment 9 and I'll get started with it. Okay, so okay, so the topics are in this week is also unconstrained nonlinear programs, and mostly the problem is related to, say, steepest descent, something related to feasible direction. Okay, so I think feasible direction is not. It's mostly on steepest descent, univariate methods, and those so on. So, but the assignment problems are mostly on steepest descent that I can notice. The first problem is on steepest descent, second is also same, third is similar, fourth is also similar, fifth is also same, sixth is also same. Yeah, next is constraint nonlinear optimization problem. So mostly with equality constraint in this week. So the week after that will be inequality constraints and so on, the KKT methods and those things. Um, yeah. So the solution method could be method of substitution. And then Lagrange's multiplier method. So mostly those things will be covered. Okay. Okay, so I'll get started with similar problems to assignment uh, 9. But yeah, so let me start with some of the concepts of steepest descent method. So what you have is that, so generally the direction that you move is, for the descent direction, it's minus of squared of fx. So that's, say, for a minimization problem. Yeah, the reason being is that if you take dt times, say, delta fx, this becomes minus fx, delta fx transpose, delta fx, minus of, say, norm of delta fx square. So this is less than 0. So that means you are decreasing your objective function value. So that's the descent direction in the minimization problem, right? So this is t equals, so this is the direction. So again, you can prove it using the Taylor series expansion. So I'm not going into the details of it, but mostly what happens is, say, fx plus alpha d, fx plus some alpha dt fx, then you have some higher order terms. So if you neglect higher order terms and just set this to less than 0 and alpha is set some positive number, then what you'll end up with is fx plus alpha d, uh, which is less than fx. So that means you are decreasing your objective function value by moving in the direction of d and taking step size alpha. So for the maximization problems, what you have is d equals some delta, say, fx. So the good thing about it is that uh, and do some similar analysis, and it will be norm of delta fx square. This is greater than 0, and again using some Taylor series expansion, it's fx plus alpha d delta fx. Then the other terms, this is greater than 0, this is greater than 0, and you'll be left with fx plus alpha d greater than fx. So you're increasing your objective function value. So that's the basic idea behind this steepest descent direction methods. Okay. So the other thing that you can have is quadratic functions. So the typical expression is that some, let me write down, qx equals half of x transpose ax, or yeah, ax plus b transpose x plus c. So as you already know, for any function, you can find the steepest descent direction for a minimum or minimization problem, or a steepest ascent direction. So this could be your ascent direction. So it's just taking the gradient and setting it to the negative of that. So you can also take the gradient here itself. And to get the gradient, so you need to have some knowledge on how to calculate it. So I won't be going into the details of it because I think you can do it yourself. So because this is a direct assignment problem, but then you have to just set it, just take the direction as minus of, say, delta qx, and that will be a solution to the second problem or something. Then the interesting thing is that you can have, so the step lengths, as I mentioned, say fx plus, say, alpha d is probably less than fx, but what should be a good choice of alpha? Okay, so for that also, I think there are expressions by which you can find out depending on the function that is given, and I think that's already done in the class. So check lecture slides to solve the third problem. Then steepest descent methods. So it's related to the points and the directions. Okay, then it could be the relationships. between the vectors. So I think that will be similar to the fourth problem. So here it's this and this. So whether it will be perpendicular, parallel, or oblique to each other, those kind of things are being asked, or whether it's none of this. So again, this one also check lecture slides. So I think this have been solved as well. Okay, so I think the first four problems will be done using this. So this could be your first topic. This could be a second. This could be a third. This could be a fourth. Okay. So the fifth thing could be uh, I'll give you a function and I'll ask you to apply the steepest descent method to get the next vector or the next to next vectors. Okay. Okay, so let me change the function expression and the initial point and try to solve it. Okay. The problem given is apply steepest descent method to minimize fx1 comma x2 equals say 3x1 square plus 4x2 square plus 5x1 x2 minus say 2x1 plus 3x2 plus 9 starting with x1 equals 1. Okay. Find x2 and x3. So there could be multiple options that are correct based on how many next points are being asked. Okay, so let me write down the function expression. So it's 3x1 squared plus 4x2 squared plus 5x1 x2 minus 2x1 plus 3x2 plus 9. Let's first evaluate the gradient. So as you all know, first you have to take the partial derivative with respect to x1 and then you need to take the partial derivative with respect to x2 as well. So first one is 6x1 plus 5x2 minus 2. Okay. The next one is 8x2 square. Sorry, not x square. 8x2 yeah, plus 5x1 plus 3. Okay. Now, what you can do, uh, you can put the value 1 and 2 here to get the exact value at that point. So this is 2. Okay. So this is 6 plus 10, 16 minus 2, 14. Then 16 plus 5, 21 plus 3, 24. I hope this is correct. Please check the calculation. So this is at 1, 2. Now the direction will be the opposite of this. So the D will be minus 14 minus 24. Now x2 is x1 plus lambda d. x1 is 1 comma 2, so this is plus lambda minus 14 minus 24. And now what you will have is 1 minus 14 lambda, 2 minus 24 lambda. Okay. Now you have to find the value of lambda. So find the value of lambda. Typically, the way it is given as lambda equals uh, S transpose S divided by S transpose AS. The S is minus D, so which is 14 and 24. Okay. So you can have this as 14, 24, 24. This is also 14, 24. A value, it's dependent on this. So 3x1 squared, so this term will be 6. Then 4x2 squared, so that term will be 8. And then you have x1, x2 terms. So that's 5x1, x2. So if I'm not wrong, just a minute, I'll check it out. Yeah, a2 is 5. Yeah, so both of them will be 5 and 5. So that's the expression of A matrix. And finally, what you have to do, so you can express it in terms of half x transpose ax plus b transpose x plus c. So find A from here. So you have seen this in the previous class, I think. So this will be a lambda value. So let me quickly try and solve this. Okay, is my screen frozen for some reason? Okay, I think it's x2 plus x1 lambda d. After that, it's frozen for some reason. Okay, I think I have to unshare and share. Just a minute. Okay, so what I did here is that x2 plus x1 plus lambda d, and I wrote that expression in terms of lambda, and I have to find the value of lambda. So this S transpose S times divided by S transpose AS is what I have to do. And S is nothing but negative of minus D, so that I have written. And A expression you can find out using the original function expression, and you can write it in terms of a quadratic function and get the symmetric matrix A. So now I have to calculate this value. So I'll just quickly do that, try to do that. It's 24 times 24. So I think it's 772 divided by, so I made a mistake. This should be a column vector. Okay, so it's 14 times 6 plus 24 times 5. Then it's 14 times 5 plus 24 times 8. So you do that. It's 204 times 14 plus 262 times 24. It's 9144. So it's 772 divided by 914. So it will come around 0.084. So x2 is 1 minus 14 lambda and 2 minus 24 lambda, right? Okay, so that means your x2 is uh, minus 40 times 0.084. Okay, yeah, so this is an unconstrained optimization problem. Okay, so it's coming out to be this. So that's x2. Similarly, you can find out x3 by just plugging in this value back to the gradient and finding out the directions, then the lambdas and so on. Find x3 similarly. Yeah, so not going into the details of doing another iteration of it, but I think you'll be able to do it. So that's the idea behind the uh, fifth problem that's given in the assignment. The sixth problem is similar. Apply steepest descent method to minimize this function, starting with this, and the steepest descent direction is S, and you have to find out that directions, okay? Uh, yeah, so in the sixth problem, okay, steepest descent directions. So find, say, S1 and S2. So there could be multiple correct answers. So here it's S1 equals D1, S2 equals D2. So D1 is nothing but minus of grad of fx at that say x equals to x1 point, and then D2 is minus the grad of x equals to x2 point. Okay, so you have to find this capital X1 and capital X2 anyway, and I'm not going into the details of it because that could be simple. The seventh problem, I'll write it down. So I'll change the function expressions. So I'll tell you that maximize z equals 60x minus 3x squared minus xy minus 4y squared plus 70y, subjected to x plus y equals 15 and xy greater than equals 0. So solve the above optimization problem by method of substitution. try and solve this problem. So what you have here is that x plus y equals 15. So you can write y equals 15 minus x, and you can replace that in the objective function. But you also have y is greater than equals 0. So that means x is less than equals 15. So 0 less than equals x less than equals 15 will be one of the constraints to this problem. And the objective function becomes z equals 60x minus 3x squared minus 6y minus 4y squared plus 70y. So this is 60x minus 3x squared minus x times 15 minus x is 4 times 15 minus x squared plus 70 times 15 minus x. So you can simplify it. Sixty x minus 3x squared minus 15x plus x squared minus 4, 225 minus 30x plus x squared plus 7. This should be 1050 minus 70x. So you can simplify it further. So that will be the first part gives you minus 2x squared plus 45x. Okay. Minus 900 plus 120x minus 4x squared plus 1050 minus 70x. So it's minus 6x squared. Then you have 1, 2, 3. Okay, so it's 50 plus 45, 95x. And then you have 150. Okay, great. So this is the expression that you have. That's minus 6x squared, 95x, so 150. So now, by the method of substitution, this problem is equivalent to minimizing 6x squared minus 95x minus 150 subjected to the constraint, which is 0 less than equals x less than equals 15. So what you can do, we can try out some classical optimization technique. So you can name it as gx. So your g prime x is 12x minus 95. That gives you x is 95 by 12, which is indeed within 0 to 15. And so that means this is your x and your y will be 15 minus x. So y is 15 minus, so that's 180 minus, okay. So the x star, y star in this case is 95 by 12 and 85 by 2. So this is how you solve this problem using this method of substitution. Okay, so let me solve another one using this. Okay, so this could be related to the 8th problem. Yeah, so I think this problem might have some issues with options. So if you find something, you can raise the issue to the discussion forum, but you can double check. Okay, but anyway, I'll solve a similar problem. Suppose I tell you minimize z equals x square plus y square plus z square equals, say, 3x plus y plus 2z, or yeah, yeah, 2z equals, say, 14. And I tell you x and z is greater than equals 0. So in this case, what you can do, you can express y in terms of x and z. So this is by method of substitution. So what you can do right now is minimize. So z, so this z is, you can think of it as capital Z. Now this z is x squared plus 14 minus 3x minus 2z square plus z square. So now it's an expression in terms of two variables. 196 plus 9x square plus 4z square minus 84x plus 12xz minus 56z plus z square. This becomes 10x square plus 5z square minus 84x minus 56z plus 12xz plus 196. And you know that, so this is your z, and you also know that x and z are greater than equals 0. So again, you can use some classical optimization technique. So you can take grad of, say, z. This z is capital Z at, say, x comma z. This could be your 20x minus 84 plus 12z. This could be your 10z minus 56 plus 12x. Okay, so then the next step would be to set this ones to 0. So what you will be left with is 20x plus 12z equals 0, and 12x plus 10z equals 56. Sorry, this is not 0. This will be your 84. So it's you can solve this system of equations and get x and z from this, and finally you can get y using the expression that you had, 14 minus 3x minus 2z. So yeah, this is how you solve this problem. So by method of substitution. But once you solve this, you have to check whether both x and z are positive or not. Check if both x comma z greater than equals 0 or not. Okay. The ninth problem will be using Lagrange's multiplier method. So this problem could be max of 5x plus 6y plus 2z subjected to some circle x squared plus y squared z squared equals 4 x y z greater than equals to 0, and I'll maybe ask you to solve the above optimization problem by Lagrange's multiplier method. Okay, so let's quickly solve it. I think I have some 10 minutes left. Yeah, some 10 minutes left. Okay. So first job will be to convert it into a minimization problem. So this is equivalent to min of minus 5x minus 6y minus 2z. And now you have to write the Lagrange multiplier or the Lagrange function. So this will be minus 5x minus 6y minus 2z plus you have only one equality type constraint. So let me write down that as lambda times 6 squared plus y squared plus z squared minus 4. Now we will be taking del L by del x, which is minus 5 plus 2 lambda x del L by del y, which is minus 6 plus 2 lambda y. Finally, del L by del z, which is minus 2 plus 2 lambda z. So this is equals 0, this is equals to 0, this is equals to 0. This gives you x equals 5 by 2 lambda. This gives you y equals 6 by 2 lambda. So that's okay. Let me keep it as 6 by 2 lambda. So the calculations will be easier. Z is 2 by 2 lambda. Okay. And also you have, sorry, del L by del lambda. So that's x squared plus y squared plus z squared minus 4 equals 0. So you can plug this here, those values, and you can get the lambda values. So this is 5 squared, so that's 25 by 4 lambda squared plus 36 by 4 lambda squared plus 4 by 4 lambda squared equals 4. So 16 lambda squared is 16 lambda square is 40 plus 25, so that's 65. Lambda square is 65 by 16, so that gives you, so now since your xyz are positive or 0, so lambdas cannot be negative, so here lambda is root 65 by 16. And finally what you have, that gives you 5, 6 and 2. Okay, this was this will be your x, y and z, and you can simplify it further if you want. Okay, So the first one, I think, yeah, simplify. I'm not going into the details. Okay, so that's why you can get this X star, this Y star, and this is Z star. Yeah, very similar problems you'll find in the assignment. And the final one, I'll just quickly give you an example. Yeah, so it could be again say minimization of minus 30x plus 4x square plus xy plus 3y square minus 20y subjected to say x plus y equals 15 and xy greater than equals 0. So what you can do here is that using Lagrange's method. So this is solve. Okay. So let me quickly give a sketch to solve this. So it's a two variable problem. So you have to write down the objective function first, and since it's a minimization problem, you need not transform it in any way. And this is lambda times x plus y minus 15. After that, what you have to do is you can find del L del x. So that's minus 30 plus 8x plus y plus lambda. This is nothing but x plus 6y minus 20 plus lambda. So lambda is 9x 8x minus y plus 30. Or you can have it as two equations. So this is 8x plus y equals, this is set to 0, this is also 0. 8x plus y equals 30 minus lambda. Here you can have 6 plus xy equals 20 minus lambda. And then you can find x and y in terms of lambda. In terms of lambda, then use x plus y equals 15 to find out lambda, and finally obtain the values of x star and y star. Yeah, so that's the step of solving these problems. Yeah, I hope this will be clear to you. So let me see. It's almost time. Yeah, it's almost time for this. Yeah, so let me just write down. Post your doubts on the discussion forum. Yeah, I think the week 8 assignment was easy, and week 9 assignment, similar problems I've already given you some sketch to solve it, and I think you'll be able to do it without any problem. And yeah, if you face any issues, you can always ask me similar problems, or you can post it in the discussion forum. So I think I'll be able to answer it. So I don't think there will be much issue with assignment 9 as well. I think just one problem which has one issue is related to the option, which is problem 8, I think. Yeah, other than that, I think everything should be fine. So yeah, and next week I think I'll be discussing more on the inequality constraints, KKT conditions, on those things, and I'll solve the exact assignment 9 problems as well, and similar problems to assignment 10 I'll discuss. So that would be the agenda for the next week. So with that, I'll stop for today, and yeah, if you have any doubts, you can always ask later in the discussion forum. Thank you all.